And at this stage, what we want to do is try to understand better the terms in this expression. Some of them you know, like capital V, that represents the beam shear, and you learned in beam statics how to find that at a point and the variation of that along the length of the beam. You learned also about the second moment of area in the statics class. So that's not new, although there's some things we want to practice with that. It's this capital Q and identifying this width B that begins to be the difficult part of applying this model. Right, so let's start with a little bit of review. Here we're going to start with an 8x3 inch rectangular beam, and we're going to ask to find the capital Q for 3 different points. Right, and so point A is at the mid-height, point C is at the outer point, and point B is halfway between A and C. Right, so that's all demonstrated down here in these 3 about where those points are at. That's not this little crosshair dot. That's this little tiny point here, a little point there, a little point there. We'll come to that. Let's start though with a review of the second moment of area. Right, we've got a rectangular cross section, and the second moment of area that we care about is with respect to the neutral axis, which for elastic behavior is going to be located at the geometric centroid. And so this very simple case, the geometric centroid is located, of course, at the mid-height. And in that case, 4 inches from the top, 4 inches the bottom for the 8 inches overall height that we've got here. And the formula we would use, of course, would be BH cubed over 12, where the B in this case is not necessarily the same B as in our model for tau equal VQ over IB, right? I know that's confusing. You have to think about context here. In this case, it will be, but it's because everything is all the same. But in other examples, you'll see where that's not the situation, right? So just play along for a while and try to understand the big picture of what's going on, and then go back and look at the small details, right? So 1/12 of this for the rectangle, the base, which is 3 inches, times the height, 8 inches, cubed over 12, and that will be how we're going to calculate what the second moment of area will be for that section, 128 inches to the 4th, right? So that would be the value that would go in for shear stress calculations for this cross section, would be that value right there, right? And the V would come from either a problem statement or having to conduct the statics analysis on the beam. All right, so what about this Q business? So let's look at that. All right, now that's the first moment of the area outbound from the point in question, right? So the point in question here, point A, is at the neutral axis. So the outbound area is all the area from here to the outer fiber. Either side doesn't matter, right? You'll actually get the same answer no matter what you do. In this case, it's sort of obvious. We got a symmetric cross section, but here now let's take a look. We've got 4 inches for that height, 3 inches for that width. So our area would be 4 times our 3, and then the centroid of that area would be 2 inches high, and so 4 times 3 is 12, 12 times 2 is then of course 24 cubic inches, length squared, times a length will give us length to the 3rd power. That would be that one. B is located halfway between A and C, so in other words, it's 2 inches up and 2 inches from the top. And so that makes that area 2 by 3. And then its moment arm then is, well, 2 up plus another inch to get to the centroid, or 3 inches. So 2 times 3 times 3 is 18 cubic inches. So it's not half like you might have thought because we have half the area. No, the moment arm is a little bit bigger. So that's kind of interesting. And then we go to point C, all the way in the outer fiber. Now here, it's at a 4-inch distance, it's 3-inch width, right? But its area is 0. Thickness 3 inches wide. Its moment arm is 4 inches, but the whole thing is 0. Okay, and that's because this is, notice as we moved up, the base got higher and higher, and the area got smaller and smaller and smaller. So that little value just kept that distance up, which we called Y1, in the derivation, right? So y1 here would equal 2 inches. Y1 here equaled 0. Y1 here equaled 4 inches. That's not the centroidal distance, just happens to be this instance. The height of this little rectangle, as we go to the limit at point C, goes to 0, and you end up with capital Q being 0, right? What you want to do is develop a symbolic equation for Q for a rectangular beam. So allow this height up to be y1 generically, and you've got this distance C, right, to the outer fiber, and come up with, if this is your width, which in this case would be lowercase b, right? At point A, the width of that little yellow rectangle is 3 inches. At point capital B, that width is 3 inches. At capital C, that width is 3 inches. If we were going to calculate in here, you'd use the 3 inches for that B here, and you'd also use it in that capital Q calculation. It would show up twice, right? So when you're going to develop the symbolic equation, go ahead and work that out and find out what kind of a variation you have in terms of this y1 distance. That's a crucial study step for you to go through. In other examples, we're going to take a look at applying this to not just a rectangular cross-section, but to some other kinds of cross-sections, so that we can see, again, how to figure out what the capital Q and capital B are.